Hello, everyone. So, I thought that this was an interesting problem to go over together, given as part of the Kinematic slideshow and video recorded by Mrs. Vorndick. And I thought this would actually be a useful one to go over together, because it seems simple, or to me, but at least like something you could just plug and chug with the formulas you're given. But there's actually a bit of trickery to it having to do with unit conversion, so I thought it would be a good example as a combination of the units we are going over. So, a car speeding at 80 miles per hour passes a still police car, so not moving, which immediately takes off in hot pursuit. Using simple assumptions such as that the speeder continues at a constant speed, estimate how long it takes the police car to overtake the speeder. Then estimate the police car's speed at that moment, and decide if the assumptions were reasonable. Assume a car can go from 0 to 60 miles per hour in 6 seconds, And yes, this should be car right here, not care. Alright, so, as I've said, it's a bit deceptive, but we'll start by writing out what we know. So, v underscore c, that's the velocity of the car, is 80 miles per hour. Geez, all over the place. But yes, so the velocity of the car initially, and we're assuming it doesn't change, is 80 miles per hour. Then we know the acceleration of the police car is given by 60 miles per hour in 6 seconds. So that translates to 60 miles per hour divided by 6 seconds, which will give us 10 miles per hour per second, or 2 miles per hour second. An hour second is an awkward unit because we've got two different units of time, so this is the first bit of trickery. Why don't we, and I think since we have two different measurements of miles per hour, let's convert this whole thing into hours. So we have 1 hour is equal to 3,600 seconds. So, as with the conversion unit, 1 miles per hour second times 3,600 seconds, so we put the seconds on top of this fraction here, or this ratio here, per hour. So 3,600 seconds and 1 hour are equivalent units, so we're effectively multiplying by 1, but in doing so we're going to cancel the second units and wind up with 36,000 miles per hour squared. So, hold on. We have the information we need to find the place where they intersect. So we're going to use this good old formula where x, your current position, equal to your starting position, plus your initial velocity times time, plus 1/2 your acceleration times time squared. And we're going to come up with equations for both the police car and the speeder. So the police car starts at 0 miles, which is just where we've assigned the origin, because it's a simple place, and that'll be the place where the two cars initially pass each other, or the speeder initially runs by. We're told that it's starting still, so the velocity of the police car at time 0 is 0 miles per hour, and then times time, plus 1/2 times 36,000 miles per hour squared, our acceleration that we found before, times time squared. And then we just get rid of the zero terms and find that our position for the police car at any time is 180,000, 18,000 miles per hour squared. So, then for the car, we're told we're starting time once again at the position where they cross each other for the first time when the speeder goes flying by. So it's also starting at 0 miles, the starting position of the police car, and it's moving at initial speed 80 miles per hour, and we multiply that by time, plus 1/2, and it's not accelerating, so acceleration here is 0 miles per hour squared times time squared. Once again, we chuck out the zero terms and arrive at the position of the car in time with respect to time is 80 miles per hour times time. Alright, so now we can find the time when their two positions are the same. So we put the car position, 80 miles per hour times time on one side, and the police car position, 18,000 miles per hour squared times time squared on the other side. Alright, so because we have time and time squared on both sides, we can divide out time. Note, when we do that, we can get into kind of quadratic equations. We've effectively factored out the t equals 0 solution. So t equals 0 is a viable answer to this equation up here, but it's not the answer we're looking for, because that's the time when the speeder first bursts past the police car. We're looking for the second time when they pass each other, when the police car catches up. So we now have 80 miles per hour is equal to 18,000 miles per hour squared times time. And that'll give us time is equal to 1 over 225 hours. That's not a very illustrative number, so let's go ahead and put it back into seconds, and we get t is equal to 1 divided by 225. Once again, now we put the seconds on top. 3,600 seconds divided by an hour is equal to 1. But we're just converting our units, so the hour cancels with the hour, and we get 16 seconds. Alright, now we want to look at the next part of the problem. Decide if the assumptions were real by finding the police car speed at the moment. So, to do that, we have to plug it back in to our equation. So, if the acceleration of the police car is 10 miles per second, or 10 miles per hour second, then it stands to reason that the velocity, or is v is equal to 10 miles per hour second times t. So we could get that by deriving, or taking the derivative of our first equation. And I chose in the first part to convert the whole thing into miles per hour squared, because I thought that helped us keep track of units and not messing up. But there's no reason we can't keep this in this 10 miles per hour second unit. We just have to pay attention to what units cancel. In fact, I'll put a parentheses around these two so that we remember that the seconds are on the bottom. So now we're taking this v is equal to 10 miles per hour second times the time we found of 16 seconds. So the seconds will cancel with the seconds, and we get 16 times 10 is 160 miles per hour. And that tells us that our assumptions may probably not be reasonable unless this policeman is rocking a supercar, because at the time, if he is able to maintain a constant acceleration, he is going to reach 160 miles per hour. I know some supercars can do like 200. My guess is the average policeman is not rocking such a car. So when in actuality, we would need to use some equation for acceleration, which is more complicated. But for the moment, we have solved the equation. Oop, everything's messed up now. We've given all information that was demanded of us, and we have our answer. So, thank you all for listening. Yep. Hope this was informative. Have a good day.